Here's another example. A ship on the ocean has mass 5,400 kilograms and experiences a force of 7,900 newtons acting at east by 19 degrees south from its motor, and a force of 1,500 newtons acting at west by 45 degrees south from the wind. Assuming these are the only forces, find the ship's acceleration. So, first thing to do, draw a diagram. Here's my ship. 7,900 newtons east by 19 degrees south. Well, if I make my axes east, west, north, south, east by 19 degrees south is this away. So that's the force from the motor. And that's 19 degrees. And 1,500 newtons west by 45 degrees south. That's over here. 45 degrees. And that is from the wind. Okay, those are the only forces that contribute to the net force. Then we can find the ship's acceleration. We know net force equals mass times acceleration. So the force from the motor, doing vector components, we can figure out that 7,900 cosine 19. The angle's from the horizontal, so it's cosine sine. East is positive, south is negative. So 1,700 sine 19. Force from the wind. West, south, so we can go cosine sine. West is negative 1,500 cosine 45, comma negative 1,500 sine 45. And we can add those together to get the components of the net force. 7,900 cosine 19 minus 1,500 cosine 45 gets us 6,408. Store as x minus 7,900 sine 19 minus 1,500 sine 45 minus 3,632. Store as y. And this is the net force. And that's equal to, we know, mass times acceleration. There are two different ways you can go about this. You could find the magnitude and direction of the net force, and then divide by mass to get acceleration, or you could divide each of the components by mass to get the components of acceleration. Personally, I'd rather find the magnitude and direction of the net force, just to save myself one division. So the magnitude of the net force is going to be 7,400 newtons and inverse tangent y over x. Positive east by 30 degrees, negative means south. That's the net force. And we know that's equal to mass times acceleration, which is 5,400 times a. So we take that magnitude of 7,400, divide by 5,400, and we get that the acceleration is approximately equal to 1.4 meters per second squared at east by 30 degrees south. Okay. Mass is a scalar, which means that when you multiply a scalar and a vector, you get another vector going in the same direction. Okay. If I took the vector 1, 2 and multiplied it by 3, I would get 3, 6. That would still have the same slope, I guess, as 1, 2. So the angle doesn't change. The angle of the net force is always going to be the angle of the acceleration, but then the magnitude you do divide. Alright. And just one more example. Two men are pushing a desk across the floor. One applies a force of 150 newtons at east by 24 degrees south, while the other applies a force of 130 newtons at east by 11 degrees north. If I punch this in, my net force, 150 cosine 24 minus 150 sine 24. And then I've got 130 cosine 11, 130 sine 11. Add them together, and that will get me my net force, 150 cosine 24 plus 130 cosine 11. Gets me an x component of 264 point something. My y component, minus 150, minus 150 sine 24 plus 130 sine 11. That gets me my y component, minus 36 point something. And then take my magnitude, square root of x squared plus y squared, 267. Call that 270 newtons at inverse tangent y over x. Positive x component is east, negative y component is south, so that's east by 7.8 degrees south. And I get the desk's mass is 110 kilograms. What's the acceleration of the desk? Well, we know net force equals ma, so 270, actually I should use the stored value, 267.10 whatever, equals 110 a, and I find the acceleration f divided by 110, not plus enter, is an acceleration of about 2.4 meters per second squared, and as I said before, the angle remains the same. So those are just some examples of how we can do forces with vector things.